with talk on the integral homology ring of 4-dimensional toric orbifolds. You're welcome.
Thanks. It's my great honor to give a talk about the recent work with Tseleung and Jongbaek. I would like to thank the organizers for giving me such opportunity. First of all, I want to say the integral cohomology ring is the ordinary cohomology ring of the when we think the orbifold as a topological spaces. I'm not talking about any other cohomology structure here. So it seems.
So there was some question in the.
Okay.
Oh yeah, now try.
Yeah. Let me first introduce the definition of moment angle manifolds following a construction due to Butcher's turbo and Panov and Ray. To begin with, I'm using the letter PD to denote a simple polytope of dimension D. And as by definition, a polytope is given by the intersection of finitely many half spaces in some RD space. So in this case, we can write a point in a simple polytope as some points in RD satisfying finitely many inequalities as we written in that way. So the Butcher's turbo panel reconstruction saying that there's naturally embedding from PD to RM with a symbol greater or equal at the bottom. So this symbol means the spaces that are in Rm such that each coordinate is greater or equal to 0. In this way, by definition, PD is a subspace in Rm. This embedding is given by just sending x to the point such that the ith coordinate is given by the number appearing in the ith inequality. So on the other hand, we have a map mu from Cm to Rm greater or equals to. So given by mu z1 dot 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 until zm to the point such that the ith coordinate is the norm of the ith coordinate of the point beginning with in Cm. So in this case, we can define a moment angle manifold as the pullback of this embedding of PD to Rm and the map mu. So this is the definition for the moment angle manifold. On the other hand, we can also identify Cm as a quotient space from Rl greater or equal to times torus, m-dimensional torus. Here Tm meaning a compact torus of dimension m. So I want to give you an idea of how this identification is. So for example, we can take m equals to 1. So we can think about the complex number, say, as this whiteboard. And on the right-hand side, before we taking the quotient, we got an R cross S1, just a circle. So imagine that we start with a circle. So this is the space. We have a circle starting on the left-hand side, and we let this circle move to the right-hand side until the infinity. So this is the R greater or equal to 0 times S1. So the quotient, namely, means we quotient out the circle begin with to quotient it to a point. So the quotient happens when we identify this circle just to a point. So in this case, we can say the complex number is homeomorphic to some infinite cone. So Cm in this case Cm is also homeomorphic to Rm cross Tm modular tilde. Is basically we repeat this identification to M copy of this one. Okay. Using this identification, we can write that P as PD times Tm modular tilde. Just restrict the Rm to PD. So that's how we think of that P as a quotient space given by the product of P and Tm. Okay. So using this moment ongoing manifold, I want to consider certain orbifold given by a certain torus acting on this manifold. To introduce this quotient space, I need some extra information called the characteristic function, which is from the set of the facets of the simple polytope P to d-dimensional lattice. So remember that d equals to the dimension of this simple polytope. And characteristic function requires that the image of each facet is a primitive vector, and when the facet meets somewhere non-empty, and their image should be linearly independent in that D. So in this case, lambda can induce a homomorphism of tori. We denote such homomorphism by exp lambda, which is a homomorphism from Tm to Td. In that case, we obtain a quotient given by moment ongoing manifold under the kernel of this exp lambda. So due to Davis Januszkiewicz, we call this quotient space a toric orbifold. Indeed, oh sorry, I can't.
Like that?
Yeah. So indeed, if we substitute that P quotient construction to this XP ZP mod over kernel XP lambda, this requires the quotient construction given by Davis Januszkiewicz construction for a toric orbifold. So let me quickly recall the quotient construction from Davis Januszkiewicz work, saying that a toric orbifold is a quotient space given by PD times TD modulo some equivalent relation. And this equivalent relation is given by xt is identified with x prime t prime if and only if the first coordinate are equal, and the t inverse times t prime lies in some torus defined by this face f. So this face is the unique face in the simple polytope which contains x in its relative interior, and the TF is the subtorus given by the characteristic function. I want to give you a feeling of how it looks like when P is a polygon. Okay, so in this example, we can say if I start with a pentagon and I cross it with a two-dimensional torus, according to the definition. So that means for each point in the polygon, I can attach a two-dimensional torus on the left-hand side. Then following the construction, I can do the quotient. So if the point lies in the interior of the polygon, I didn't quotient out anything. All the torus attaching to the point in the interior will survive in the quotient space. But if the point lies in the interior of the edge, I quotient out a one-dimensional circle, which is generated by the characteristic vector. And if the point is exactly one with the vertex, I quotient out all the whole torus to a point. So this is a picture to describe a four-dimensional toric orbifold, how it looks like. Okay. There are many calculations works describe the cohomology ring structures of those quotient space. So first of all, if K, if we're working in rational coefficient, think if the space, the quotient space is a manifold, in that case, the equivalent cohomology run of the space is proved to be the Stanley-Reisner run associated with the simple polytope. And in that case, the cohomology run is isomorphic to the Stanley run modular and ideal determinant by the characteristic function, which we denoted by J. Because I'm care about the integral cohomology when xp lambda is a orbifold, the known results are focusing on the cohomology by assuming the order dimensional cohomology vanish. So in that case, date back to 1973, Kawasaki computed the case of weighted projective space. So if we use gamma k to denote one generator for a 2k dimensional of this weighted projective space, in that case, he described the car product in terms of the coefficients arising from this characteristic function that defines this weighted projective space. In general, otherwise, a result given by Franz and Popo, he showed that the cohomology run is isomorphic to the equivalent cohomology run tensor with a copy of Z. So by their result, we can say that if we want to know the cohomology run of the space, it is enough to know what the equivalent cohomology run is. So then almost 10 years later, Barry, Saka, and Song, they define, they gave a description of this equivalent cohomology called weighted Stanley-Reisner run, denoted by omega SRP lambda. They describe some criteria of certain elements inside the Stanley-Reisner run, and show that equivalent cohomology run is isomorphic to certain subrun in the Stanley-Reisner run. And following the result by Franz and Popo, the cohomology run of the of toric orbifold is isomorphic to this quotient run from weighted Stanley-Reisner run over this ideal J. So the question here is, although we can define a weighted Stanley-Reisner run, given a pair like a P and lambda, it is not known what the generators and the relation, what the generators for this run, weighted Stanley-Reisner run, except for a few examples. So, for example, if our P is a triangle, and if the characteristic vector is given by 1, 0, 0, 1, and AB, so in this case, the Stanley-Reisner run over a triangle is a quotient with a quotient run given by a polynomial run with 3 generators, and the ideal is given by the facets that has trivial intersection. So for the case of triangle, so only the 3 edges E1, E2, E3, their intersection is empty. So in this case, we quotient out the ideal generated by x1, x2, x3, and you can work out the weighted Stanley-Reisner run and modular the linear ideal generated by J. And in this case, we can find the 2 generators. W is given by AB x1, and Z is x2, x3. So I use this bracket to denote they are quotient out under this linear ideal J. So using the run structure of the Stanley-Reisner run, you can describe the product of omega square equals to AB Z. So that's how we use a BSS result to describe the product for the toric orbifold. we want to consider any arbitrary polygon instead of just like a triangle here. Before we talk about the ring structure, let me recall the cohomology groups for a four-dimensional toric orbifold. So, so this is the Fishley did calculated the cohomology groups in 1992 in his thesis using the language Toric varieties, and later on Kuwata, Masuda, and Tseleung, they considered a larger family of orbifold called the torus orbifold, and the result showed that for a four-dimensional toric orbifold associated with an n+2 gon, such that the ith edge is associated with a primitive vector given by ai bi. So in this case, the cohomology groups is already known. So for example, the two-dimensional cohomology is has Betti number equals to n, and the third cohomology is a torsion element where the order is given by the GCD of all the determinants from different edges, and the four-dimensional is one copy of that. So for dimensional reason, the car product, non-trivial car product, only lies in the degree 2 elements. Okay, so this is the cohomology, the group structure for a four-dimensional toric orbifold. So we considered a special case by assuming there exists a adjacent pair of edges such that the determinant of these corresponding characteristic vectors is equals to 1. So by changing a basis, we can assuming there exists one pair of edges such that the characteristic vectors are 1, 0, and 0, 1. So in this case, our main result is showing that there exists a basis of 1, U1, UN, and V from the cohomology, where U1 and UN, they are degree 2, they are basis for the degree 2 cohomology, and the V is a generator for the degree 4. The car product UI with UJ equals to AI BJ V. So here AI BJ comes from the characteristic vectors. So there's a consequence of this result. So we also showed that if the cohomology of the four-dimensional toric orbifold has no two torsion, then the cohomology ring can distinguish the homotopy type of the spaces. So in this case, if we consider any particular two spaces X satisfy there's a pair of characteristic vectors which are 1, 0, and 0, 1. In this case, if two such spaces are homotopy equivalents, if and only if the matrices formed from the car products are congruent over Z. Okay. So in the remaining time, I want to talk about the ideas about proving, showing this calculation. So first of all, from the homotopy theoretical point, according to a result by Barry, Schumann, and Song, such toric orbifold can be understood as the mapping cone from some map F from S3 to n copy of wedge of two-dimensional spheres. In this case, we can applying the long exact sequence to the cofiberations to denote to get a UI to be to denote UI to be the dual of the ice copy of two-dimensional sphere, and V is the basis given by the full cell. So in that case, we obtain a cellular basis for describing the cohomology of this space. We can directly applying Hilton-Miller theory to show that up to homotopy equivalence, F is given by some linear combinations of some white-hat maps and hopeful maps, and we can further to show the car product between UI and UG, which is exactly the coefficients appearing in the white-hat map, and the car product for the UI with UI. This is the coefficients is exactly given by the hopeful map. But one thing is from this homotopical theoretical point of view, we can obtain a cellular basis, but it is not clear how this Cij and the Ci is related to the characteristic matrix. On the other hand, as we know the formula from Barry, Schumann, and Song, using the weighted Stanley-Reisner, the advantage of using weighted Stanley-Reisner is once we know two elements in weighted Stanley-Reisner, we know how to multiply them together because it is a subring from the Stanley-Reisner. But the difficulty using that algebraic model is we don't know how to find a basis or how to find a set of generators in that algebraic model. But using this homotopy theoretical point of view, we can get a basis, but we don't know how to describe the product structure. Then our idea is how do we relate this cellular basis to some elements inside the weighted Stanley-Reisner, so we know how to do the product structure between cellular basis elements. In order to do that, we use a tool called toric morphisms. Toric morphism, the idea of toric morphism is to consider the morphism between two spaces that are equipped with the torus actions such that the morphism is equivalent with the corresponding torus actions. Because our toric orbifolds are constructed from a polytope and acting torus, so we want our morphism are induced from the maps from a polytope and a torus. So for example, if I starting with a polygon, I can contracting several edges leading to another polygon which has smaller edges compared with the polygon I begin with. And I can fix the TD to TT by taking just identity map. So if we look at the example, in that case, if I just skip the edge associated with the characteristic vectors 1, 0 and 0, 1, if I keep the ice edge AI, BI, namely I contracting the red edges to the red colored vortex. I contracting the blue colored edges to the blue colored vortex. So this is a continuous map, and this I take the product of this edge contraction map and the identity map on the torus. This is compatible with the quotient relation. So in this case, this continuous map can induce a map on the corresponding toric orbifold. So second example is I can fix the polytope. So for example, if I got a triangle, I can fix the triangle, map the take the identity map on the triangle. Then I take a group homomorphism between the tori. So once I know it is compatible with the quotient relation, this continuous map can induce a map on the corresponding quotient space. So in this way, as I said before, edge contraction can allow us to start with a polygon, choose another polygon with less edges. Okay. The good thing is we can do computations using these two types of toric morphisms. For example, in the case of edge contraction, I get a continuous map between one 4-dimensional toric orbifold to another 4-dimensional toric orbifold associated with a triangle. I can using the naturality of this map to get the induced map on the cohomologies. So on one hand, I have a cellular basis. Using because edge contraction is particular maps, I know how the cellular base are mapped to what kind of like cellular basis element. And on the bottom, the algebraic model, we can also do the explicit algebraic calculation at the bottom. So in this case, in this way, in order to do the car product in any toric orbifold associated with an n+2 gauge, it is enough to understand the ring structure from the toric orbifold associated with a triangle or a square. So this strategy works fine if both sides of the spaces are toric orbifolds. But there's one special case. For example, if I start with a square with 1, 0, 0, 1, 1, 0, 0, 1. So in this case, if I want to contract any of the edge, it gives me some 1, 0, 0, 1, 1, 0, something like this, right? So in that case, I have one point with two edges associated with two characteristics vectors. They are identity. So this does not satisfy the condition for a characteristic function. In order to fix such problem, we generalize the definition for a toric orbifold in the polygon case. We call it is a degenerate characteristic pair associated with a polygon. So in this case, the function from the edges to the 2-dimensional lattice, we do not require the linear independence condition. We only requires AI, BI to be a primitive vector. So in this case, we can similarly define a quotient space given by P2 times T2 modular the tilde relation. This tilde relation is similarly defined when the point is not a vertex, but when it is a vertex, we still quotient any point in the T2, regardless whether the corresponding characteristic vectors are linearly independent or not. So I think moreover, we can study the homotopy types of the resulting space. So for example, if we are given an n+2 polygon, and suppose we are given a lambda function from the edges to Z2 such that there exists a pair of adjacent edges that have identity characteristic vectors. So without we can assuming lambda E1 equals to lambda En+2. So in this case, we can consider another P prime, which is an n+1 gone, and such that lambda prime EI equals to lambda EI. So in this case, the homotopy type of YP lambda is given by YP prime lambda prime with another 2-dimensional sphere. So for example, in the triangle case like this, and like 1, 0, 0, 1, 0, 1. So in this case, the resulting space is homotopy equivalent to S2 wedge S4. So it is obviously from the homotopy type, we know how the product structure is. So in this case, we can using the product structure on triangle or any squares for including degenerate toric spaces to resolving the product structure for the toric orbifold we start with. So I think I'm running out of time, and sorry, I finished a little bit rush in the end. 1 minute. Oh, okay. Sorry that I will stop here. Thanks for your attention.
Okay, thank you. Any questions or comments?
Could you show one of the first slides?
Uh.
Where you describe relations in cohomology. I cannot understand. Okay.
This one.
Next. Okay, next. It's okay, next.
This one.
Okay, next. Okay, next. Oh, yes, next. Okay, next. Where is French? Next.
This.
Next.
We don't have.
Next. It's this all.
Yeah.
Because okay. Because you remember there was such a relation I B I, and then we write down. So you see A I B J.
Oh.
And then you consider AGBI. What it is for strange for me. Okay. You remember when you describe the relation?
It's AIBJ.
You have generators.
Yeah.
AI
Yeah.
and BG.
Yeah.
Show me exactly.
I think here AIBJ.
It's okay. What before?
Нет, на следующий, next, maybe next slide.
No.
Там было разница.
Напиши.
Next slide.
Да нет, на доске.
Вот это, внизу там последняя строчка.
Yes, you see.
GCD of,
You see. AIPG minus
AGBI. So it's the determinant.
это числа, это определить.
It's the determinant from two pair of these characteristic vectors. So it's AIBJ minus AJBI. Yes.
Okay. It is a great common division. Yes. It's okay.
Yeah.
So, look at, okay. Of course, it is a commutative algebra. So,
Oh, this is the torsion. Sorry, this is the torsion. This is the order for the.
That's interesting. Towards the last slide, you had this. Could you show this concept of degenerate toric orbifold? That's quite interesting one there. So yeah, you have that. Once you have the coinciding vectors in the characteristic function, you say that you just split off two-dimensional.
Sorry, I'm nervous. Sorry, I forgot to mention the idea how to get this homotopy equivalence. Is basically we start with any. Let's say, if we have this space, right? This is some. Let's call it some singular, singular vertex. So originally, this is the.
Yeah, that's what I saw.
Moment. Yeah. Moment ongoing manifold. So this is S4. So we can, because any polygon are homomorphic to each other, so we can think of, I take a vertex, they're supposed to be a torus, here. So we can think of just quotient this torus to a point. So that's think of the cofiber from S1 embedding into this space. So
S1
this
embedded into S4.
Yeah.
And that's a wedge. Yeah, that's very nice. But
yeah,
apparently you have a similar concept for in higher dimensions. So once you have some coinciding vectors in the characteristic function, or just when the determinant is, do you have some? This is a nice example, but do you have the kind of a general construction for this in high dimension? When you have a characteristic function with determinant is 0 over Q, yeah. So do you have kind of a concept of doing something similar on describing this homotopy type for this somehow degenerate toric orbifold?
I wanted to do this, but I wanted to understand how it can be used for describing the ring structure. I haven't formulated any formula for the high dimensional thing, but yeah.
Right.
Yeah,
that's
yeah.
You turn to page where you have computed the cohomology of a four-dimensional cell complex.
Yeah.
The previous one. The previous one.
This one.
No, the previous one. Yeah. Oh, okay. Is this space a manifold? XP2 lambda.
In general, it's an orbifold.
Is a orbifold.
Yeah.
Not a manifold.
It is a manifold.
But I guess if it's homology at degree 1 is there, then it is a Poincare complex.
Yeah.
The diode here
But
inside.
because the main result we did is for computing the product structure.
Yeah. So what's the intersection form of this four-dimensional complex?
What's the sorry?
Intersection form.
Once you got this matrix, for example, this matrix is the intersection form for this four-dimensional space. Right. The intersection form H2 tensor H2 goes to some number Z. So this is exactly given by the car product, right? So the matrix we obtained by choosing the nice basis, right? Nice basis. This matrix is the intersection form.
Yeah. So it can be can be any two vector. Yeah, texts.
Not you have to choose a basis, otherwise the product formula, and because linear map.
Is there a standard choice so
No,
that the signature of this complex could be fine?
I don't know there's a standard way of doing. In the manifold case, I think the signature already computed, right?
What's the manifold case? What's the signature?
I can't remember. Is it? It's in one of their papers. I can look that for you, the formula, but I can't remember now. I can look for the papers written. I think it's written somewhere.
Any other comments or questions? Okay, let's thank the speaker. Okay. It was the final talk for today. Now you have time for dinner. You can have dinner in dining room, but for dinner you have to pay. And the transfer bus will be